Hello and welcome back. So in this video, we will look at the so-called active contour models or snakes. So one of the systematic kind of PDE-based models to have come out of calculus of variations, and one of the pioneering methods in the in that class of methods, the pioneering work. Okay. So, like I said before, it's a pioneering model using calculus, variation calculus to determine curve evolution. So, why is this so important? Because previous techniques or the techniques that came before this were all typically based on heuristics, like a bunch of rules that you put together and hope that it worked. But in this one, this is of course used. When I say this is used for segmentation. It actually, the rules actually came out of variational calculus. By putting together a correct choice of data terms, a loss function, and regularization terms in the functional, we arrived at a curve propagation equation without having to explicitly specify rules. Okay. So here, when I say data term and regularization term, I urge you to think back about the Brachistochrone problem, where we looked at whether we go fast by dropping vertically down a bit so that time is reduced, or we reduce time by going the shortest path. So that was the tension there. Here there is a tension between data and regularization terms. Okay, we'll look at this in more detail in the next few slides. Okay, so why are they called snakes? So if you consider any object, okay, that is to be segmented, in this case an organ to be segmented in a scene or an image, in the medical image. The boundaries are basically the curves, the boundaries of objects or the curves, and that's how we seek to segment objects by propagating closed curves so that they can go and latch on to the boundaries of objects. Now, what is the other characteristic of the boundaries of object? Typically in a medical imaging setting, the boundaries are characterized by high gradients, that is sharp changes in pixel intensity values or brightness values. Okay, so ideally the curve that we are propagating, that is we are trying to latch on to the boundary, should also coincide with regions of high gradients, right? So that is one of the important criteria that is considered in this method, right? So we have right away we are looking at the various terms that go into the functional. So first we discussed that the gradient is an important term. So the gradient will tell you where sharp transitions in pixel intensity occurs, and we surmise that wherever there are sharp transition in pixel intensity means that there is a change in the regions, right? That's the edge of the object that we are looking for. So we a priori don't know the object, but our hypothesis is that the edges of those objects correspond to regions of high intensity, and we want our curves to go and rest or latch on to regions of high intensity. So that's the one term. So that's the term that you see here, negative gradient squared. Okay, so that means that you have you are looking for regions of, why is it negative? So where the gradient is high, it means that it's a very high positive value, so you put in a negative sign there so that it becomes a very small number. So you minimize, so it becomes a very small number. So you're trying to minimize our functional. So one of the terms in the integrand is this, that becomes a very small number when the gradient is very high. The other terms that we want really small are this. So here this is where the tension is, because we want them to latch onto the gradients, but we want them to be smooth, or they won't be smooth curves. Okay, so this is your regularization term, which makes your curve smooth. Of course, there are various explanations for this, but I'll just give you a couple here. So what this term does, this delta C or delta S, I'll tell you what these variables mean. So this is the first derivative, right? The square, there's a square there. So make sure it's always we are dealing with positive numbers. The square. So the delta C or delta S makes sure that you don't have very sharp discontinuities in your curve. Okay, and what this also ensures is that you have a very tight curve, or basically your curve is as small as possible. Okay, so it doesn't have sharp discontinuities, and it's generally trying to be a very curve. When you say short as possible, the length of the curve is shortened. Okay, this is the length shortening term. So that's the first derivative. This second term This is just to make sure that the curve is not too wriggly, right? So you don't want some, so there, if you have an object, let's say, that's the object that you are trying to segment, okay, and your curve, right, you don't want some curve going like this. This is what we saw. You don't want a lengthy curve, right? So this is a very long curve, right? And this term makes sure that these sharp discontinuities don't occur. Rather, you have a smooth curve, right? A fairly shortened curve. The second term, what it does is make sure that you can also have curves like this. So you have abrupt changes in the first derivative. So this is what this happens. Just make sure that your curve is not super wriggly, it's more smooth. Okay. So what are these? C is the curve, obviously, because it's just a notation. What is C of S represent? Okay. This is just some parameterization. So S is a parameter that goes from 0 to 1. Okay. I'm sorry. I'm just writing it in a very poor way. Let me just wipe this off. So S belongs to 0, 1. So it varies S very smoothly from 0 to 1. So it's a parameter which generates the curve. Okay. So S is a so your curve, your parameterized curve by S. Okay. C of S, basically it just means you can think of it as generating X of S. C of S is nothing but a pair of points, X of S and Y of S. Okay. So X and Y are basically points on the curve. So you think of a curve, it's in a plane. X and Y are points on the curve, and you can generate the curve by varying S smoothly. There are many parameterizations available. We won't go into that. So, for instance, you can think of S as maybe cosine theta and sine and for instance, X can be, let's say, R cosine theta, and Y can be R sine theta. This is one parameterization. You can put R to be 1, so you get only cosine theta, sine theta, and you can actually vary theta, right? So you can of course normalize it so that theta varies from 0 to 1 and then you multiply accordingly, right? So those things can be done, right? So that's S is just one parameterization like that. So there are lots of parameterizations available. Don't have to worry about that now. We'll cross that bridge when we get there. So C of S is nothing but it's a vector of these points, X and Y, right? It's a collection of X and Y which make up the curve. So that's what we always, when we say C, we are only looking at this bunch of points, X comma Y. One second, I'll just wipe this out and yes, much better. So you have these points, X comma Y. So you can generate them, right? So you have X1, Y1 up to Xn, Yn if you discretize it, if you choose to discretize. Otherwise, it's a continuous parameterization. So S smoothly varies from 0 to n so that you can generate all the X and Y's possible, right? So infinite number of X and Y's possible, which make up the curve. Okay. So there are these two terms. One is, like I said, the negative of the gradient squared, the gradient of F here. F refers to the image. Okay. Here we can use I, but typically it's a bad choice in this kind of work. F refers to the image. C of S here, it basically we are evaluating the gradient only at the curve. So at all the points that make up the curve, we are evaluating. That's why it's F of C of S. Okay. So the gradient, so for the curve to be optimal, so if you want the curve to latch on to the object boundary, we stipulate that at the points wherever the curve is, you want a very high gradient. Okay. Which means that if you take a negative of the gradient, which means a very large negative value, which means a very small number there. So the minimum. That's why we're trying to minimize that. Okay. So large gradients, and we want the curve to be smooth. Okay, so which means that's why we are adding the first and second derivative terms. These are called regularization terms. Okay, so these are the two competing forces that we have talked about, right? Like the shortest path, highest velocity, high speed path. We are looking at, it has to latch on to strong gradients. At the same time, it should not be too big a curve or too long a curve, and it should also not be too wriggly a curve. Okay, so that is the tension here, and of course we are trying to minimize this following functional. We add this E internal is this energy which corresponds to the regularization term, and this I call the data term because F is the image, that's the data that's given to you, and you are trying to estimate the gradient from the data. So that's the data term. So and here and in the paper they have referred to as an external term. Okay, E internal energy and the external energy. I like to call it regularization and the data term. So there is just a interplay between these two terms. Typically, you will have these parameters alpha and beta here. Okay. Now alpha and beta can depend on S also, or they can be independent of S. Either way is fine, and they are the terms that gives you the ability to control how much importance you give to each of those terms. Okay, so by making alpha and beta small or zero, you can make their influence small or larger. Okay, so that's the idea. So that's the entire loss function. So that you put them into the loss functional, and you're trying to minimize the loss functional with respect to what you are trying to estimate C of S, like we had for the curve in the Brachio-Stokes problem. Here we are trying to estimate the segmenting curve C of S, which will form the boundary of the object. So once you have the boundary of the object, we can find the interior also. So we are trying to estimate C of S, or alternatively, since C of S is nothing but collection of these points x comma y which make up the curve, we are trying to estimate a bunch of x comma y, right, which form the boundary of the object by minimizing this functional. Okay, so and of course remember, S is the parameterization of the curve. S varies continuously from 0 to 1, and as S varies continuously from 0 to 1, you can generate x and y as you will. Okay, all right. So likewise, just to get a better understanding of the snake's functional, consisting of three terms. Like I said, the first term, the data term, the curve should coincide with high gradient regions, which typically form the boundary of the object. So in medical imaging, also in a lot of situations, the boundary does form. The boundary does have high gradients. Okay, it's sometimes in the paper they refer to as the external energy term. Okay, the second term is the regularization term. Penalizes the first derivative. So it means this typically leads to a smooth short length curves. There is no without kinks, right? Suddenly there will be going to be a kink. So it has smooth short length curves. So this is a curve shortening term, right? Okay, so it will just collapse the curve into a point if there is nothing stopping it. The third term, also the regularization term, is again penalizes the second derivative of the curve with respect to arc length. I say with respect to arc length, but yes, it's basically some parameterization. This prevents excessively wiggly curves. Okay, that's what we want, right? Go back, sorry to do that. So there are two terms, right? So the first derivative term, second derivative term. So you have some function, right? If you will see that there is an energy term, I call it the energy term. There will be this f gradient of f. It depends on C of S. So it's a function of that, right? You also have the it's the your function, the integrand inside the functional is has the C prime term and the C double prime term. Okay, here the C is implicit in F. Okay, so these three terms are there, and so then you have the form of the equation you know to use to Euler-Lagrange equation to use in order to derive. So I had used F of CS. Okay, ideally, think of just don't use F. Maybe you just use this E. Okay, this F is basically because I've used this F inside the functional when you're trying to derive the Euler-Lagrange equations, right? So then that can be a bit confusing. So feel free to, instead of F, use some other symbol so that you don't get confused. No, I'm not, but so now sorry about this spelling mistake. It's couple of methods, not couple FO methods. So we're going to be only looking at the second one, right? This here numerically solving the Euler-Lagrange equation. So we'll derive the Euler-Lagrange equations. Of course, I won't go through every step because some of the steps are just calculating derivatives. Okay, so I urge you to do that. Once you know what the Euler-Lagrange equations are, you know what F is, and there are two. There's again, like we saw here that we the curve propagation equations for this. Bear with me. Usually problem. Okay. So if you actually apply, so remember, just to be clear, I think I'm using this F too much. Okay, so I'm going to just switch notation a bit, because if you look at the, I'm sorry, I have to go back and forth, but when you're trying to do the derivation. So when you actually formulate the Euler-Lagrange equation, this is what you will get. Okay, what you will get. Okay, so now, how are you going to solve this problem? Okay, so again, gradient of V external C of S equal to, I'm just using this term as it is, gradient with respect to x and y actually, right? That's what you will have. So, and these terms will only with respect to s and delta s, and the second derivative with respect to delta s. In fact, second and fourth derivative, right? 1 over delta s and 1 over delta s square. Ideally, this alpha should be inside, because if it's a function of s, you can take that out. But assuming it's constant in this case, okay? So, what is it? Now, we have to understand this. So, the way to solve this, you have to, of course, you have to solve it. There are no analytical solution. So, you have to solve it using numerical approximations. Okay. So, I urge you to go and actually derive this. Okay. It's not, you just have to plug in the correct function expressions in the Euler-Lagrange equation that you saw in the previous video. Okay. And then you can get to this very quickly. It's not too hard to do. Okay. How do we discretize this? Okay. So the discretization scheme is what I've shown you. So if this is the curve, the blue points are the discretization. So S of I minus 1, there you take, let's say, capital N points. You discretize with capital N points, and you can then you in fact you have to choose it so that they are equidistant apart. Typically, that's how it's sampled. This length and this length are the same, even though in my picture they are not drawn to scale. Ideally, you choose those points, N points on the curve for a discretization, so that they are they are equally spaced, and of course the first and last points coincide. Okay, that's your boundary condition. The first and the last points coincide. Okay, and the way you calculate the derivatives with respect to s, any parameterization is that you actually use your discretization itself. So, for instance, the first derivative with respect to if I can zoom in a bit. Allow me to zoom in a bit. It might get tilted, but allow me to zoom in a bit. So the first derivative is calculated by it's finite difference approximation. So d delta c or delta s at si is nothing but c of si, which means the c of si is nothing but the xi comma yi at that point minus c of si minus 1 divided by h, where h is the distance between these 2 points at these 2 points that you have discretized. Okay. So that's the first derivative. Similarly, you can write down for the second derivative also. This again if you're using if you do some numerical analysis, these are standard formulas. Similarly, for the second derivative of the curve at si, you have this formula, right? Again, I have made a mistake here. It's not r, it's c. Okay, I think once again. I was referring to multiple textbooks, and I was trying to use C because it seems to be more commonly used than R. Somehow it slipped in there. Sorry about that. So H is again the distance between successive points. Okay. Now these are for the first and second derivative. What you do is you take this and you plug it back in these equations. So now you are going to calculate delta over delta S of delta C over delta S. Now you have delta C over delta S, that formula here, right? That formula is right there already. Seem to have sorry, there is something I've done which I need to take care of. Okay, now it's done. Okay, so now you have delta C or delta S, the expression for this. Now you have to do delta over, okay, I have put 1 over delta S, but I should have put delta over delta S. I'm sorry. There seems to be again a mistake here. We'll correct that. So delta over delta S of here, this is delta, also this delta S of delta C over delta S. Now what you have to do is, in order to do this, you instead of C of Si, you just put delta C or delta S. C of Si minus 1, you put delta C or delta S. That's it. Or you can directly use this formula. But better still, directly use this. Delta or delta S. So because alpha is not a function of S, you are assuming it to be constant. If you assume it to be constant, you directly plug this in this equation. For the second derivative again of the second derivative, for every instead of C of Si plus 1, you have to substitute delta square C of delta S square at I plus 1, and delta square C of delta S square at S of I, and delta square C by delta square at I minus 1. So again, I seem to change this. You plug this in there, write down these expressions, and you can simplify. Okay. Once again, if I am not, I've chosen to simplify it. We can look at it later time. In practice, you can also discretize the functional itself. So it's possible to do that straight away. The original expression we had, the functional expression, we can discretize that and then take the derivatives then. based on the discretized functional. So if you do that, we end up with the following set of equations. Okay, you can actually derive them. It's very not too hard to do. Again, I urge you to do that. And if we find time, I will go through this in slightly more detail than what I'm doing now. So you will end up with this set of two equations. Okay. Again, the E is basically the image term, right? It's the gradient of the image evaluated at the curve. A is a pentadiagonal banded matrix, which basically carries the weights of the the finite difference terms. Okay, and these are the two simplified or the final form for the Euler-Lagrange equations. Now that we have this, what do we do, right? So it's not done yet. So this just gives you some way of some relationship between, or like I said, the tension between how you move the points, because A is the regularization matrix. You can think of it that way. A is the matrix that regularizes your curve. Delta E, delta X gives you the gradient information. So just like this tension between the two. So how do you propagate the curve, right? That's what we are going to look at. So, but it's not done there. What we have to do is something called gradient descent, right? So because what we have learned, right? Remember that at the optimal position, right, of the curve, once the curve has latched onto the boundary of the object, then the curve no longer moves, right? So which means that this delta C or delta T equal to 0. But this delta C or delta T equal to 0 is again that's how we have defined the equilibrium position. So which means that we are tracking the time curve over time. Okay, tracking the curve over time. So we can also, so if you think about it, if you want to evolve the curve over time, then we can actually do this so-called gradient descent. Okay, so if till we find the optimal position, we have to evolve the curve. And how do we evolve the curve? We evolve the curve in the direction of increasing gradient, which is what the minus delta J tells you. Okay, that's how you propagate the curve. So delta C or delta T is minus delta J is just the gradient descent equation. So you are propagating the curve in the direction of the opposite of the direction of increasing gradient, which is basically the gradient of the function. That's what we have, because we are trying to estimate the curve itself. So we have delta C or delta T is minus delta J, and minus delta J is what we estimated here. This is minus delta J, these terms. So then we can write this delta C over delta T as time stepping. So this again, you do a finite difference approximation. Like I said, C of S is nothing but pairs of vertices x comma y. So then we can get this time stepping equation right here, which we can simplify to get the equation in this final form. Okay. So A is a matrix that can be, there is again a small confusion here as to why I put x of t plus 1 here, but I put t there. Okay. So this is called a semi-implicit formulation. Okay. Because the way to look at it is you propagate the curve, you move the curve based on the gradient equation at the current time step, and then you move it, and once you move it after you move it, then you regularize it. Okay, that's what we are doing. So it's semi-implicit. It turns out it has much more desirable numerical convergence properties. So this is again techniques borrowed out of numerical analysis. So this is actually a very complicated method to actually understand and code. So you start with calculus of variations, you form the correct functional where there is a tension between how smooth your curve has to be or regularized your curve has to be, and how badly you want it to latch on to the gradients in the image, the curve to latch on to the gradients in the image. And then from there the Euler-Lagrange equations come out, but they are non-trivial to solve. So you solve them by using the semi-implicit numerical analysis technique. Okay, and of course you have to discretize these things properly. Okay. So what are the advantages of this thing? So the curve evolution equations emerge automatically for Euler. You didn't do anything other than intuitively decide this, right? You intuitively decided, I want a smooth curve and I want it to be attracted to gradients. Okay, that's the condition you imposed. And the rules for moving the curve around, the mathematics for moving the curve around came out automatically. Of course, it's very complicated, but still it does came out, right? And and think about this. This actually provides a framework where you can incorporate multiple forces or other energies. Okay, and of course you use convex terms, which basically something that has only a global minima. But again, we won't get into that. So you add terms which are amenable to easy to differentiate and don't have too many local minima. Okay. So you can like add more forces to make it move faster, etc. We'll see a couple of them, not in detail, let's mention them. They're called balloon forces, and there's something called the gradient vector field. Okay. What is the disadvantage? It converges to local minima. Why would it converge to local minima? If you take any image, if you think about it, yeah, a lot of images will have noise, and noises are typically high gradients. Okay. So which means that a curve can latch on to a noisy pixel or a group of noisy pixel which might not correspond to the object of interest in the image. Okay. And improper initialization can cause slow convergence. So typically this method is kind of sensitive to initialization. You pretty much have to start very near to the boundary that you want to segment. You might say that's no fun. Why would you want to do that? It's better than drawing by hand. If you have a large number of images to annotate, it's best that you start you initialize this and it automatically converges to the boundary. Okay. Now it's difficult to code because you have to keep track of all the points. Okay, that's a double-edged sword, because you don't have to keep track of for an entire image. You're trying to segment an entire image. You have to keep track of only a finite set of points. You don't have to keep track of every pixel. Keep track of every pixel. Okay. However, keeping track of each of these points, because you are propagating them, is hard because you don't want them to converge to one point. You don't want them intersecting. All these are much more difficult programmatically to enforce. Okay. So there are variants of this. I will not go into the details. If I find time, I will. There is something called a balloon force. Remember, the first derivative term makes the curve shrink. Okay, but sometimes you want them to blow, to expand a bit based on certain image statistics. So that is possible. That has been done. It's called a balloon force, which lets the curve move in any direction, expand and compress. Okay, the gradient vector field. Also remember, see, sometimes image is pretty smooth, contains maybe one or two objects, but away from the objects there is no strong gradient. So if you initialize slightly further away from the boundaries of the object, your curve will never converge. Okay, so it will just keep moving very slowly. Of course, if you continue to do time stepping for thousands of time steps, then maybe it will converge, but that's very slow and not practical. So something called a gradient vector field, wherein you think of it as smoothing the gradients from the edges away from it, right? You have a very strong edge, but then you can maybe smooth it a bit so that the gradient values are kind of dispersed around the object a little bit further than the boundary on either side. So that lets the things converge smoothly. Again, this is accomplished. This is non-trivial to accomplish. You have to solve one more, functional. You have to derive one more functional, and you actually formulate the Euler-Lagrange there, and then you get a gradient vector field which you use for propagating. Okay, so this is kind of two-step. Kind of think of it like a two-step problem. But again, this is very popular, and people have used it very effectively, right? Because for a long time these methods were there. Only ones which can be used without too many heuristics, because for every image you can't make up heuristics, every modality you can't make up heuristics. This comes from very simple sound principles. Okay, so thus this concludes our overview of snakes. Like I said, some of the derivations I have skipped. I have showed you the general principle. So you can plugging into the Euler-Lagrange equations, actually taking the derivatives is not too hard. If you have done +2 mathematics, you should be able to do. The only tricks there would be there's a discretization, etc. You have to actually work out. Again, that's also not too hard. Some of these discretization, like the only two formulas you need to know are the ones I showed you, and that you should be able to do. Okay. All right. So we will end this class here, and we'll look at further development on this, because like I said, the disadvantage is keeping track of the snakes. Right? It's hard a problem. So how do we get over that? That's where we run into level sets. Okay, so we'll talk about that in the next lecture.